you want to do here. I mean, I've got something prepared to talk in general about our subjects that we're dealing with today, but we can also talk about this. We can talk a little bit about this exercise now. We can also talk a little bit about it. We can, we'll have a session at the end of the day after we get. So what's going to happen today? You guys have a schedule, but we're going to just talk for another 20 minutes here, chat, and then you guys are going to go to a variety of activities that you're going to do, like half-hour activities that involve electrostatics, like you've just been doing. It's going to involve magnetism. We're also going to talk a little bit about circuits and understanding. One of your activities will be about hooking up batteries to light bulbs and understanding parallel and series circuits. So you'll mess around with that. And we'll also talk about electromagnetism, how electricity and magnetism are related, which is a little deeper, a little more complex, and really cool subject, understanding the connection between electricity and magnetism. And also, I think, so Alice, are we going to try to do Van de Graaff before, we don't need to do it right this second, but we'll do it in the next 15 minutes or so? Okay. So let me just start a little bit talking about this, what charges, what electricity and magnetism are, and then maybe in the process we'll just get a conversation going about what you just did. One of the things I think is important, you guys saw, some of you that came to the first session we had, the work I do is, I deal with molecular scale stuff, so I really like bringing it back to this way of looking at it. That one of the things you got to keep in mind, even doing an exercise like this tape exercise, is to recognize that everything around us, the air, the table, your body, the projector, is made up of atoms and molecules, right? Everything is made up of atoms. And what are atoms? What are atoms made up of? What are atoms made up of? All right, neutrons, protons, and electrons. And what do we know about those objects, those particles? Right. So in some ways, what we're most interested in today in is the positive and negative, right? So the electron has what kind of charge? Okay, so the electron has a negative charge, and the proton has a positive charge. So even a water molecule, this bigger protein, it's made up of these atoms, but inside those atoms is a whole bunch of positive and negative charge. I mean, you have an enormous amount in your body of positive and negative charge. Matter of fact, if you separated, this is an exercise I have my students do in my nanoscience class. If you took all the electrons in your body and put them over here, and you took all the protons in your body and put them over here, the force of attraction would be like the weight of the sun. It would be enormous. So there's a huge amount of energy, there's a huge amount of potential energy and attractive force there. Okay, so you have these electrons. So this is a really simple model of an atom. You have electrons out here. This is what's called the Bohr model, but it's kind of a simple model of what an atom looks like. You have a nucleus that has positive charge, and then these electrons are on the outside. The reason this is important for today, I mean, I'm not going to get into atomic physics and chemistry today, but what's important to understand is that the electrons are the things that are loose and can move around. Okay, the negative charge is really what does the moving around in your exercise here, and in when you make circuits, what's going to be actually doing the moving around is the electrons. What happens, the way you get positive charge is the electrons move away, leaving behind a positively charged thing, right? You have a neutral atom. This atom would have the same number of protons and electrons, so it's neutral, same number of positive and negative charges. But if electron goes away, it's charged, and then it'll leave behind a net positive charge on the atom. Okay, the only reason I'm bringing this up is I want you to remind you that, even in these cases where we have an uncharged object, like you had in this exercise, it's got charges in it. They just add up to no net charge. Does that make sense? Okay. The other thing that's kind of funny, and it's another concept that I want to try to get across to you today, is there's also this idea of magnetism. Where does magnetism come from? We're going to get into that in some of your exercises. This particular exercise you just did had nothing to do with magnetism. But So where does magnetism come from? What do people, what is the source of magnetic properties?
I'm sorry, the spin.
Okay, that's actually a really good answer to that. Do people understand what she's talking about?
No. Can you say it louder?
So all the electrons around the atoms, as they're like moving around in their cloud, they're also spinning on their axis, like the planet. And so that's, I can't go any further than that. All I know
Well,
is
that's a deep explanation, but that's actually correct. So if you have, so what it really comes down to is magnetism ultimately has its source in charges. I mean, this is all that the universe is just made up of these things. There's nothing more to it, right? It's just atoms. This is it. This is the whole universe is made out of these things. So magnetism must be coming out of this thing somehow. And what it's coming out of, these are charged particles, these electrons. And it turns out when a charged particle moves, it creates a magnetic field. So an atom itself can act as a little magnet. So in a ferromagnetic material, a permanent magnet, what you have are particular kind of atoms that you have actually are little magnets themselves. The atoms within a ferromagnetic material are permanent magnet.
And they're all lined up.
And in that case, they're all lined up. All those spins are lined up. So you all familiar with the fact that currents, like if I put a battery, if I hook up, and you guys are going to do this, if you hook up a battery to a wire, what's going to happen? Current's going to move around, current flow is going to move around, and it turns out that anytime you have current flow, there are magnetic fields that get set up. So moving charge creates magnetic fields. All right. I mean, part of what I'm doing here is I'm giving you a little bit of introduction to some of the activities you're going to be doing. You're also going to be setting up electric motors, which kind of act on this kind of phenomenon. You pass current through a wire that creates a magnetic field that pushes off another magnet, and it ends up turning motors. All right, I think I'm getting ahead of ourselves a little bit. Let's talk a little bit about that exercise. What do you think? What were the results? I want to hear from this group. So what results did you guys get? We have 2 pieces of tape, or we have 1 piece of tape, and we pull it off of the table. What do we find? When we take 2 off the table and we put them next to each other, what do we find?
they repel each other because they're both charged.
Okay.
They both have the same charge.
Okay, so does everybody agree with that? So when you take 2 pieces, so what the answer was when you take 2 pieces of tape and you press them against the table and rip them off, they're now charged. And when you brought those 2 together, what happened?
They repel.
They repelled each other. So what does that tell you?
They have a similar charge.
They both had similar charge. Does everybody agree with that?
Yes.
Mm-hmm.
All right. So when you do, so then the next stage is you take, well, first of all, what do we think's happening? We talked a little bit about this, yes?
I have a pretty good idea, I think. So the table and the sticky side of the tape are trading electrons, and or this non-sticky side. I'm not really sure where I am on that yet, and then so now the tape has a surplus of electrons, and so it now carries some sort of charge. The other tape does the exact same thing, but because they have the same charge, they don't like each other, so they repel.
Okay. What do folks think about that? So there's this idea that electrons, there's charge that's moving from one object to another. It's a little bit weird, but that's the hypothesis that's been presented here. How do people feel about that hypothesis? Okay, so which direction do we think it's happening?
So if there's more electrons in the tape, then they would either come from the sticky side to the non-sticky, or from the table to the tape itself.
Okay.
But in either case, it's coming from not the sticky side.
No, we don't do it.
Okay.
No, it's good. It's good. So, all right. So the next stage of this activity is you put one piece of tape on top of the other piece of tape. All right. And then you labeled them top and bottom. What did you find in that circumstance? What did you all find?
They did like each other.
Yeah, they were, the top and the bottom were attracted, and then when we did the two sets of top and bottom, the tops were down and the bottoms were down.
Okay. So what does that tell? What does that tell you at this point?
That the top and bottom had, one was positively charged and one was negatively charged.
Okay. Is everybody in agreement with that? Why? How does that happen? I mean, why would
Because
They're
they're
having
trading.
different experiences.
Okay, well, why are they having different?
Like the tape, the sticky side on the bottom is receiving charge from the table, and the top piece is receiving charge from the slick side of the top piece.
Okay, so that's another important point. Are the two sides of the tape the same?
No.
The two sides of the tape?
Like two sides of the tape?
Like the sticky and the non-sticky, you mean?
They were, I think that they were. I think
No, I'm not asking about charge. I'm just saying, are they in a materials
No.
sense?
The
Are they the same?
consistent, the same.
Where's the difference?
I found out that I was wrong about something, because I just made the common sense assumption that the sticky part of the tape was going to pull electrons off the table, and was going to then have a negative charge, but it seemed that in further investigation that it seemed to have a positive charge instead.
So how are you telling which is positive and which is negative? I mean, that's interesting that you've come to that conclusion. So I'm
Well,
not sure.
Because we tried with rubbing electrons off the hair, and as something else to test it against, and found out
Okay.
when you do that the electrons on this new object, were attracted to the tape that had been pulled off the table. Now, in the first experiment,
Yep.
so the table that the first one that ripped off the table apparently was positively charged, because you put electrons from the hair next to it.
So your assumption here is, and so your assumption is in the hair circumstance, you are pulling
Electrons off of that, yeah.
Okay. And so this is great because you're actually, in some ways it's hard to determine which is positive, which is negative. It's kind of arbitrary. But if you have a charge object that you know is positively or negatively charged, you can do that. So that's great. So you found that the sticky part of the tape was losing electrons.
This right here should be positively charged. When you put it next to the electrons from the hair, they come together.
Yep.
If this had positive, which I thought pulled charges off the table, this should be positive. Hair positive should push away, but they didn't.
So the table's pulling charge from the tape rather than the tape pulling charge from the table.
Apparently, that's what it seemed to be from what I was able to determine. That, yeah, when you pull this thing off, I thought it was going to pull a lot of charge off the table.
But when you say charge, you mean positive charge?
Electrons.
Okay, but that would be negative charge.
Pulling electrons off. Yeah, so there should be electrons on the tape.
Okay. But
If
you found the opposite was true.
the tape seemed to be positively charged, because when you put it next to the, this rubbed against the hair, not this, but another object,
Yeah.
they would come together. So this should have electrons from the hair.
Right.
This, if it had electrons from the table, should be the same and push, but they didn't.
Now, ignorant question, but how do you know that hair is positively charged? It's just a fact. Or what?
Don't. But, it seems like, that's the common thing. Electrons should rub off more than, protons are not going to rub off. Electrons rub off.
Well,
But what's interesting, I think the word in and of itself, electrons, I've always thought electric, so I've thought positive. And I think that's what we're forgetting, that electrons have the negative.
yeah, that's just a convention.
Yeah.
But let's remember that when you rub two things, even if you rub hair,